Deep inside the roaring heart of a steel furnace, there's a hidden chemical war going on. It's a high-stakes fight that decides whether the steel that builds our world is going to be incredibly strong or dangerously weak. Today, we're going to pull back the curtain and see how it's won.
And really, it all boils down to this one question. I mean, think about it. The difference between a bridge that lasts for 100 years and one that fails can come down to just a few unwanted atoms. So how in the world do steelmakers conquer these invisible enemies?
All right, let's meet our two main villains, sulfur and phosphorus. If you leave sulfur in there, it causes something called hot shortness. The steel literally cracks and tears itself apart when you're trying to shape it at high temperatures. Then you've got phosphorus. That causes cold shortness, making the final product brittle enough to snap at room temperature. You can see why both of those are just total deal breakers.
To put this into perspective, for the really high-grade steels, the kind used in the most critical jobs, the amount of these impurities has to be less than, wait for it, 0.015%. That is an absolutely insane level of precision. So the real question is, how do you pull that off in a giant, roaring furnace?
Well, the battle takes place inside this beast of a machine, the electric arc furnace, or EAF for short. This thing is the modern workhorse of the steel industry, and as you're about to see, its secret weapon is its flexibility.
See, unlike the old-school methods that start with raw iron ore, the EAF is basically a giant, super-powered recycling plant. It uses these enormous graphite electrodes to create an electric arc, we're talking hotter than the surface of the sun, to melt down tons of scrap steel. And that right there is what gives steelmakers an incredible amount of control over the whole process.
And here is our story's unsung hero, slag. It might not sound very glamorous, but it's everything. It's a molten layer of custom-designed oxides that floats on top of the liquid steel. Think of it like a chemical sponge. Its entire job is to seek out and soak up all the bad stuff we want to get rid of. Honestly, mastering slag is the real secret sauce to making clean steel.
Okay, so let's get into the first battle. Our initial target is phosphorus. The game plan is simple. We've got to get it out of the steel and lock it away inside that slag for good.
So how do they do it? It's a neat little two-step dance. First, you blast oxygen into the furnace. This oxygen reacts with the phosphorus and turns it into an acidic oxide, P2O5. Then comes step 2. You create a basic slag, one that's really rich in lime. And you know what happens when an acid meets a base, right? They grab onto each other. That basic slag acts like a magnet for the acidic phosphorus oxide, and boom, it's trapped.
But for this to work, you have to follow 3 golden rules. You need a highly basic slag, you need tons of oxygen, an oxidizing atmosphere, and this is the interesting part, you actually want lower temperatures. That's because the reaction itself creates heat. So remember those 3 things: basic slag, high oxygen, low temp. They're going to be important.
Okay, so we've got a handle on phosphorus. Awesome. But this is where things get really tricky, because now we have to deal with our second villain, sulfur. And the rules for this fight are completely different.
And here's the big conflict. To get rid of sulfur, yes, you still need a basic slag. That's the one thing they have in common. But everything else, it's the polar opposite. You need a low oxygen environment. We call that a reducing atmosphere. And you need high temperatures, because this reaction actually needs to absorb heat to work.
Hey, don't just take my word for it. Look at this graph. As the iron oxide in the slag goes down, which basically means there's less oxygen around, the rate of desulfurization just skyrockets. The data couldn't be clearer. Less oxygen means way, way more effective sulfur removal.
So we have a huge problem, right? The exact conditions you need to get rid of phosphorus are completely toxic to the process of getting rid of sulfur, and vice versa. It's a chemical catch-22. So how on earth do steelmakers solve this puzzle?
Let's just put it all side by side. It's so stark. For phosphorus, you want an oxidizing atmosphere and low temps. For sulfur, you need a reducing atmosphere and high temps. You simply can't do both at the same time with the same slag. It's like trying to freeze and boil water in the same pot. So the solution has to be something else.
And the answer is just brilliantly logical. They don't do it all at once, they do it in stages. First up is the oxidizing period. They set up the furnace perfectly for phosphorus removal. High oxygen, basic slag, lower temps. Then, once that slag has soaked up the phosphorus, they literally tilt the furnace and pour that dirty slag right off. It's gone.
Then they start the reducing period. They build a brand new slag, this time one designed for sulfur removal, low oxygen, high basicity, and they crank the heat. For the really high purity stuff, they'll even pour the steel into a separate vessel called a ladle furnace for one last, super precise finishing touch. You know, there's a quote from our source material that just nails it. The author says, "There is no other process of steelmaking which can compare with a basic EAF in its ability to remove sulfur from metal." And that's it, right there. The EAF's ability to switch between these two totally opposite chemical environments. That's its superpower.
So why does all this complex chemistry matter? Because this incredible precision is what allows us to make the advanced materials our modern world is built on. We're talking about the steels that make our cars lighter and safer, the pipelines that won't crack under enormous pressure, the super strong alloys for our bridges and skyscrapers, and even the ultra-clean steel needed for defense and aerospace. All of it depends on winning this chemical battle.
So it turns out that making something as common as steel is this beautifully complex dance between opposing chemical forces. It really makes you wonder, doesn't it? What other everyday materials are hiding a whole universe of science, just waiting to be explained?